Right, this is Maths Linear Algebra Tutorial 7, question number 5. Today we'll talk about the following questions from Lay. We are here to answer true, false, as well as to justify each answer. The given A matrix is an m by n rectangle matrix and B is Rm. So the problem is the problem of Ax equals to B, where A is an m by n matrix and B is an m-dimension vector. In the first part of the question number 5 from exercise number 17a, the question is, the general least squares problem is to find an x such that Ax is as close as possible to B. So we are asking for, is the problem to solve for x such that B hat minus B, the actual B given, the norm, is as close as possible. And actually it is true. It is the square norm is as close as possible. So this is the least squares solution. So the first question, 17a, answer is true. You can also refer to the course notes for details. Go to 7.1.3, page number 2, and read the theorem 6.4.1, in which it was stated that the projection of B onto the space of the W is the best solution. There is no other choice of W that will give a better least squares solution. We now turn our attention to question 5, 17b, where the problem is now stated as a least squares solution of the equation Ax equals to B is a vector x. So we are basically finding x such that when Ax hat equals to B hat is the orthogonal projection of B onto the column space of A. And the answer is this is also true. You should see the readings from section 7.1.3, page number 3, figure 2 on the right side. We'll now turn to this figure. In this figure, it shows that the normal equation derived, which gives rise to the least squares solution, is actually the same solution as this. B hat is the projection of B onto the column space of A, and the residual, which is the error here, is orthogonal to the column space of A. Thank you. We now turn our attention to question number 5, 17c. The question asks, a least square solution of Ax equals to B is a vector x hat such that B minus Ax is less than or equals to B minus Ax hat. This is false. The reason being that the equality sign should be this way around. For the reading, let us go to section 7.1.3, page number 2, in theorem 6.4.1. Let's go to the lecture slides now. 7.1.3, page number 2. The theorem states that the least square solution is less than all other solutions. So we have to be a little bit careful here of the less than. Let us now first accept that it is less than when the column space of A is independent. There is no other W that will be better than the least squares solution when the column space of A is independent. Let's now turn our attention to question 5, 17d. Any solution of A transpose Ax equals to A transpose B is a least squares solution of AX equals to B? The answer is true. And please refer to section 7.1.3, page 3 and 4 for the discussion. We'll now turn to these two slides. To understand why this is true, first read the normal equation's derivation, in which we found that the normal equation is this. In the following statement, it then says that the solution of equation number 3, which is denoted by x hat, which is found by A transpose A minus 1 A transpose B, is a solution of the least squares. And here we are also told that the least square solution is x hat, and it will bring the projection of B onto the column space of A, resulting in the error being orthogonal. What you have to realize is that sometimes columns of A is not independent, and when columns of A is not linearly independent, then maybe we cannot solve for this using the normal equations, because A transpose A inverse does not exist. We can find other ways to solve for this, and the answer is that it still will be the least square solution. In fact, we have encountered this exact case in this tutorial number 7, question number 2. Oh, scratch that. It is question number 3. In question number 3, we are asked to solve for this A given this B. We found that actually the columns of A were dependent. We then managed to solve for this equation even though A transpose A is singular by performing Gaussian elimination. And after Gaussian elimination, we could get the particular and the general solution of x hat. In conclusion, we still have to form the normal equation and solve for x. Whether the solution is unique or not depends on whether the columns of A is independent or not. Now we attempt question number 5, 17e. The question states, if the columns of A are linearly independent, then the equation AX equals to B has exactly one least square solution, and the answer is true. Please refer to section 7.1.3, page number 4, theorem number 14. We will now turn our attention to this slide. This is page number 4, theorem number 14. In the slides, the theorem number 14 states that if the columns of A are linearly independent, then basically A transpose A is invertible, and when A transpose A is invertible, a unique least square solution, meaning x hat is unique and exists. So this is the end of question number 5, 17a to 17e. Thank you.